The ratio test is looking like a great test. Does it always work? Let's recall what the ratio test says. I'm going to be considering a series, the sum of a sub n goes from 0 to infinity. And I'm going to assume that all of the terms that I'm adding up, all of the a sub n's, are non-negative. So a sub n is greater than or equal to 0. And the ratio test tells me to consider the limit of the ratio of subsequent terms. So I'm taking the limit as n approaches infinity of a sub n plus 1 over a sub n, and I'm calling that limit L. And then what does the ratio test tell me? Well, the ratio test tells me that if that limit is less than 1, then the series converges. If that limit is bigger than 1, then the series diverges. But if the limit is equal to 1, then the ratio test is inconclusive. So what happens when L equals 1? Well, supposedly, the ratio test doesn't say anything in that case. But if we listen really carefully, is there something that we can get out of the ratio test even when L equals 1? No. Whoa, okay, but why not? Well, there are cases where L equals 1 and the series converges, but then there are also cases where L equals 1 and the series diverges. Can we actually see some of these examples? Well, here's an example, maybe kind of a silly example, of where L is equal to 1, but the series will end up diverging. So let's try this. Here is the example. It's the sum, n goes from 0 to infinity, of the number 1. Which, I mean, this definitely diverges, right? If you keep adding up 1 plus 1 plus 1, right, that's not a finite number. So this is a divergent series. But of course, in this case, what's a sub n? Well, a sub n doesn't depend on n. It's just always 1. And so the limit of the n plus 1th term over the nth term as n goes to infinity is just 1, because a sub n plus 1 and a sub n are both 1. And what about an example where the series converges even though L equals 1? So I want an example where the L in the ratio test is 1, but the series ends up converging, even though the ratio test doesn't tell us that. So let's see an example. An example of this is the sum n goes from 1 to infinity of 1 over n squared. This series we've already seen to converge. It converges by, let's say, the p-series test. It's a p-series where p equals 2. But what is L in this case? Well, the nth term in this series, a sub n, is 1 over n squared. So L is the limit of a sub n plus 1 over a sub n as n goes to infinity. And in that case, that's the limit as n goes to infinity of 1 over n plus 1 squared divided by 1 over n squared. And that limit is indeed 1. But how do I know that this limit is 1? Well, to compute this limit, I could first rewrite this as the limit as n approaches infinity of 1 over what? I'm just going to move the n plus 1 squared in the denominator, so it'll be n plus 1 squared over n squared. Now I could expand out the n plus 1 squared. This will be the limit as n approaches infinity of 1 over n squared plus 2n plus 1. That's what I go and I expand n plus 1 squared divided by n squared. And now this is a sum here in the numerator, so I could split this up into 3 separate fractions. This is the limit as n goes to infinity of 1 over n squared over n squared plus 2n over n squared plus 1 over n squared. And I could simplify this a bit more too. This is the limit as n goes to infinity of 1 over n squared is 1, 2n over n squared is 2 over n, and 1 over n squared I'll just write as 1 over n squared. Well, what's this limit? When n is very large, this is very close to 0, and this is very close to 0. So when n is very large, this is 1 over 1 plus a number close to 0 plus a number close to 0. This limit is 1, which is exactly what I'm claiming. So when we say that the ratio test is silent when L equals 1, it's not for a lack of understanding. There really are series that converge and series that diverge, and in both cases, L equals 1.